Yes, yes, I have started recording.
Okay, so this is P and C. This is M belongs to A belongs to M and C, so that A is positive definite. Similarly, P and R is equal to A belongs to M and R, so that A is positive definite. So last theorem which we have proved in, I think, in the last class, exponential map from Hn plus P and C is a homeomorphic. And also we have shown that exponential map from symmetric space or symmetric matrix to PNR is also homeomorphism. Okay.
So
No.
Muna, as I remember, you mentioned that these are not Lie groups. That's set of positive definite matrices,
Yes,
right?
yes, yeah.
So
These are not.
what to do with this exponential map? How is it useful? You show that it's a homeomorphism.
Yeah, you will see later. Okay.
Okay.
So this thing is we want to derive some conclusion. So see, the thing is Hn. I have told you this is a real vector space. Hn is a real vector space. Now that means Hn is topologically homeomorphic to something like R to the power D, where D is the dimension of R over Hn. This number is not important, but you can calculate that. This is with something like n square. Okay, so this is homeomorphism. Now we have Rd, and this is homeomorphic to Hn, and this is homeomorphic to P and C. And this is map is exponential map. That means we are getting that Rd is homeomorphic to PNC. So is it clear? Rd is homeomorphic to PNC. So now we have got that Rd is homeomorphic to PNC. Now this implies PNC is path connected, and not only path connected, and it is also simply connected. So you will get that fundamental group of PNC is nothing but trivial. Yes. By similar argument, similarly, we will get R to the D is isomorphic to P and R, where D is equal to dimension of Sn. Here this is symmetric matrix over Sn. This number is not important, but I am writing this. So this is also imply that P and R is simply connected, path connected. And fundamental group of P and R is trivial. So now, now I want to prove an important theorem proposition. Okay, so let fix fix k belongs to n and k greater than equal to 1. Okay, suppose A is positive definite, then there exists a unique B belongs to N C, so that B to the power k is equal to N. Moreover, B continuously depends on N. And if I can add that real thing to this, okay, so let us see. If A belongs to PNR, then B also PNR. This statement precisely says that you can define some kth root of a positive definite matrix. Okay, so let us. So this is statement is A is a positive definite matrix, so there exists a unique B belongs to P and C, so that B to the power k is equal to A. Moreover, B depends continuously on A. And last thing is, if A is a real positive definite matrix, then B is real. This is the symbol for unique. Actually, I hope you know. Okay, so proof is very simple. Proof as A belongs to P and C, so there exists unique T belongs to Hn, so that e to the power T is equal to A. I will define B is equal to e to the power 1 by kt. Okay. Since 1 by kt belongs to Hn, and we have seen that exponential maps Hn to Pnc. Therefore, B belongs to Pnc. Okay. So now what is e to the power k? This b to the power k is e to the power 1 by kt to the power k. This is e to the power t. This is nothing but a. Okay. Now I want to do uniqueness. Okay. Suppose there exists another b tilde belongs to PNC with b tilde to the power k is equal to A. Now, as b tilde belongs to PNC, this implies there exists unique S belongs to Hn with e to the power S is equal to b tilde. Now I have this thing. Okay, so let us do a phase space. Okay, this thing is clear, right? Okay. This is b tilde to the power k is equal to A. From previous page, b tilde is equal to e to the power S. So I will replace that e to the power S to the power k is equal to A. So e to the power ks is equal to A. And we also know that e to the power t is equal to A. Okay, so both S and T, ks and T belongs to S. Since both ks and T belongs to Hn, and we have we know that this by okay, you know that this if something this function, this T is actually unique. So by previous theorem, actually not previous theorem, and T is equal to Ks. That implies S is equal to T by K. So this in so what is B tilde? B tilde is equal to your e to the power S. So this is e to the power T by K, and this is I am getting, so B tilde is equal to B. Now further, if okay, so you know that this exponential map from Hn to Pnc is a homeomorphism. Therefore, this T will depend continuously on A. Therefore, hence B will also depends continuously on A. Okay, so this is also clear. Since T continuously depends on A, this implies B is equal to e to the power T by K continuously depends on A. Now, if A belongs to P and R, we have seen that this T belongs to Sn, symmetric matrix. This is real matrix. This implies B is also e to the power T by K. This is easy to see that this belongs to P and R. So this finishes the proof of this thing. Okay. So this precisely says that in the set of positive defined matrix, we can define the nth kth square root, kth root. Okay. So now I want to really fix k belongs to z, this belongs to n, and k greater than or equal to 1. I define this tk from MNC to MNC by tk of A is equal to A to the power k. Now I will get one corollary from the previous proposition. This tk from PNC to PNC is a homeomorphism. Okay. So and tk from PNR to PNR is a homeomorphism. Just wait 1 second. Okay. So I hope this corollary is clear to everything. Now I want to define some important things which is called polar decomposition, and this is the most important theorem, one of the most important theorem in this classical polar decomposition. First is let A belongs to GL and C, then there exists unique U belongs to UN and P belongs to P and C. Is unique. P and C, so that A is equal to UP. Moreover, U and P depends continuously on A. So it has a second part. That A belongs to GL and R. Then there is unique O belongs to orthogonal group and unique P belongs to P and R. So that A is equal to OP. Moreover, O and P depends continuously on A. So let us first concentrate to the first theorem, that this says that A is a complex invertible matrix. Then I can write that A is equal to UP, where U belongs to unitary matrix and P is a positive definite matrix. And this decomposition is unique, and U and P depends continuously on A. So what we will do, we will first prove the uniqueness. Then after that, you will that uniqueness will give some idea about the decomposition. Then you will use that idea and will see that this we will finish the proof of this theorem part A. Okay, proof of part I. Okay. Proof. So of I, suppose A is equal to UP. So this is actually I just wanted to say that there is a strong analogy between this matrix Lie group and this so-called theory of semi-simple Lie group. Actually, you will see that if if something is an isometry of non-compact Riemannian symmetric space, and we have a polar decomposition, and that proof actually follows this pattern actually. So it is really very important to understand this matrix Lie group. So I hope you will pay some attention to it. So A is equal to UP. So I write this A star is equal to UP star. Okay, so this P, since P star is equal to P, I write P U star. Okay, so there is for this A star, okay, A star A, then P U star U into P. Okay, this is A star, this is A, so this is called P square. So I am getting this P square is equal to A star A. P square is equal to A star A. So I am demanding this P is in a positive definite matrix, and I know that A star A is also positive definite. So this means, and I have shown you that for a positive definite matrix, there exists a unique square root. So since we demand P belongs to PLC, so that will implies P has to be the unique positive definite square root of A star A. Since A star A is positive definite, since so once P is fixed, then U has to be fixed, because we have to really A is equal, since A is equal to UP, then U is equal to AP inverse. So once P is fixed, then U is fixed. This implies U is also unique. Uniqueness is clear. Okay, so now decomposition existence. So so take P, so take P is equal to the square root of A star A. This is the unique square root of A star A. So this implies P square is equal to A star A. So A has U has to be defined by AP inverse. I have to only show that this U star U is identity. So let us see that. So what is U star? This is equal to A P inverse star. That is P. Okay, P star inverse into A star. But P star is equal to P. This is P inverse A star. Okay. So now take U star.
No, just a minute. So
Yeah.
A is any matrix in GL and C, right?
Yes.
Then you took A star A, and then you took the square root of that.
Yes.
Okay.
That is the unique square root of,
It is
and
the unique square root.
P belongs to P and C. That's what I mean here.
Okay, so A star A will be Hermitian, right? That you are using somewhere.
A star A is Hermitian and positive definite.
Positive definite. Okay. Oh.
That I know. This is easy to check. A star A is positive definite.
Yeah, yeah.
So now can I proceed?
Sure.
So P has to be this. Therefore, U is equal to AP inverse. U star is equal to P inverse A star. Just simply. So I want to check that U is unitary, right? Is it okay, Manoj? I want to check U.
Yeah.
U star. So this is AP inverse and P inverse A star. So this is A P to the power minus 2 A star. But I can write that that A P2 inverse A star. Now P square is equal to A star A. So P square I put A star A inverse A star. So I got here A, okay, A inverse, okay, A star inverse A star. So I got this is identity. Okay. So I got the polar decomposition. Okay. Now I have shown that this square map P A going to A square is a homeomorphism on this positive matrix, space of positive definite matrix. So clearly, so since A going to this, okay, A star A to the power half is continuous. So this implies this T continuously depends on A. So since U is equal to AP inverse, this implies U also continuously depends on A. So this is a very this finishes the proof of this fact. So now I need to finish the second thing. If A is equal to PNR, what will happen? So we will just look at the proof. So you have to replace this U by some O orthogonal matrix. Okay, then you will take transpose everywhere. Instead of A star, you will take A transpose, and we will always remain inside real matrix. Okay, and we have shown that if and you will get that there, in that case you will get that P square is equal to A star A, and we will get that P is a real matrix, and you apply the same argument exactly. So, okay, so you will then second also will be clear. So proof will follow by applying, say, okay, that's the same argument, and this is also clear. Okay, so now this finishes the proof of polar decomposition. Now I want to really draw some important contour. So first, polar decomposition. So polar decomposition, and I want to draw. First thing, you notice that you have got this GL and C. This is equal to some UN and P and C. This is homeomorphism. You now this UN, you can write that this is equal to e to the power some HN. Okay, since and this is also homeomorphism. Everything here actually homeomorphism. Now this is topologically isomorphic to UN cross e to the power r to the power d, where okay, so let us write one step further. So since this exponential is uh, exponential from Hn to Pnc is homeomorphism, this is topologically equivalent to Un cross Hn, and this is Un cross some r to the power d, where d is equal to dimension of Hn over r. Okay, so what does this mean? This means, okay, since Un is path connected, this implies GL and C is path connected. This is clear. So you will, moreover, you will get this fundamental group of GLMC is equal to fundamental group of UN. This is clear. Okay, Pritam, is this clear?
Yes, yes.
Okay. So now I want to say about the second thing. So GLNR is your ON cross PNR. Okay, so this is ON, and this all this equality means homeomorphism. Okay, so e to the power, this is Sn. So this is homeomorphic to On cross Sn. This is On cross R to the power D, where D is dimension of Sn over R. So since we have proved that On has two connected component, so this implies GL and R has two connected component. Okay, and in this case actually, since actually you know that this as a fundamental group is only defined for path connected spaces, so it doesn't make sense to say that fundamental group of GLNR is fundamental group of ON. Okay, so this is the thing. Now third thing is important thing. Suppose I take this group GL plus NR. So I want to say how this what is the means polar decomposition will look like. Okay, so let A belongs to GL plus NR. So by polar decomposition, this is the real matrix. So this implies A is equal to some orthogonal matrix O.
So what is this
into
notation? This is positive determinant.
yeah. So let's write that. This is equal to A belongs to GL and R. So that determinant of A is greater than 0. So O e to the power A, where A belongs to Sn, right? Now you have to use this fact, determinant is positive, so I take determinant on both sides. Determinant of A is equal to determinant O, and determinant of e to the power A.
Why same A?
Oh, sorry. Sorry, thanks. Sorry, I some S letter right. Okay. So determinant of A. Okay. So this is determinant of O and determinant of e to the power s, e to the power trace of s. Okay. So that will determinant of it. Now look this carefully. So this is positive. This is positive because see this this is a real matrix. Trace of s is a real number. So this is trace is positive. So this will imply determinant of O is positive. But O is orthogonal matrix, so that implies determinant of O is equal to 1 since O belongs to orthogonal matrix. Now, so this implies O belongs to SON. Okay. So you will get that in this case GL plus NR. Okay. This is equal to SON and e to the power SN. Okay. Under restriction of homeomorphism or homomorphism, you will get that this is 1, 1, and 2 and everything. So that means GL plus NR. Okay, since we have seen that since SON is path connected, since SON is path connected, this implies GL plus NR is path connected. Okay. Now, you know that this, sorry, if I have defined this, if I tilde is equal to diagonal of 1, 1, 1, last into minus 1, this GL minus NR, this is the matrix with negative determinant. So this is I tilde into GL plus NR. Here actually let us define GL minus NR is, this is the notation you GL NR, so that is negative. So this is okay. So this is this implies since GL NR is, this implies GL minus NR is also connected, is path connected. So you will get that. Okay, so we have proved that GL and R has two connected, and I am getting GL plus NR connected and GL minus NR is path connected. So I want to draw the conclusion. So this GL and R has two connected components, and the components are precisely GL plus NR and GL minus NR. Okay, this is the third example we are looking at. So fourth example, let us look at SLNC. So you take so let A belongs to SLNC. That means A is equal to some U into e to the power h, where h belongs to Hn. Okay, so that it will imply that you take determinant in both sides. Determinant of A, so determinant of U in determinant of e to the power h. Okay, so this is equal to 1. Determinant of U, determinant of, sorry, this will be e to the power trace of h. So Hermitian has since S belongs to Hn, this has H has real entries in diagonal, right? In diagonal. entries in diagonal. So trace of H is real. This implies trace of H is real. Comes to R. So this implies this is positive. So this implies determinant of U is positive. But as U belongs to UN, so determinant has mod 1, so that implies determinant of U is equal to 1. And this implies U belongs to SU. So now, okay, so look at this. So U belongs to SUN. So look at this equation star. Okay, from star, we get this 1 is equal to determinant of U is equal to 1 into e to the power trace. H. So that will imply that trace of H is equal to 0. So this will imply that H belongs to small SLNC. This is the definition of SLNC. If you have worked out that exercise, that if trace of H is equal to 0, then H belongs to SLNC. So we are getting that what H belongs to SLNC and U belongs to SU. Okay. So what I am getting, so final conclusion is I am getting like this. I am getting SLNC is equal to what? SUN, and this matrix H belongs to SLNC. This will be e to the power HN intersection small SLNC. This is the polar decomposition. So this is equal to SUN. Topological, this is SUN into some R to the power D, where D is equal to dimension of HN intersection SLNC. D is equal to dimension of R. So I will get that since SUN is connected, path connected, in fact, let's apply the SLNC is path connected. And is fundamental group of SLNC.
Mona, I have a little doubt. It may be obvious also. So, you have shown that HN is some kind of RT, right? When you are
HN,
taking intersection with SLNC.
This is a vector space, real vector space HN. And SLNC is a vector space, real vector. So intersection of this is a. Okay, so I should have written. Okay, what? Okay, so let me write this. So what I'm saying that from here it's from star. Actually, look at this star. Okay, SLNC is equal to SUN into e to the power HN intersection SLNC, right?
Yeah.
And this exponential map is also a homeomorphism. Okay. So SLNC, you will get this. Okay, so this is isomorphic to SUN into this whatever that HN intersection is SLNC, right?
Yeah.
And this is a real vector space. Because intersection of two subspaces are real. So this is SUN intersection some R to the power D, where D is equal to this dimension of RHN intersection SLNC. Is it clear?
Okay. Thank you.
So that for that reason I am saying that pi 1 SLNC is equal to pi 1 of SUN. Okay. So, okay, this is the thing. The fourth thing I might give you to exercise also. So fourth IB 4 point, you can take this an exercise. Okay, so you will get this SLNR. Okay, Okay, so is equal to, you exactly do the same way. This is SON to the power. This you will get this SN intersection small SN. Okay. Now I want you to really light. Okay, so this implies. Okay, so you will get this thing. So that will imply that this is topologically equivalent to SN. So N into SN small n R. So this is topologically equivalent to SON into some R to the power D. Since SON is path connected, so epsilon R is path connected. So this is clear. Now, as I said that in the beginning, that compactness is always easy to show. So these are all non-compact groups. Okay. Okay. So these groups are non-compact, and I'm just saying that. Okay. So summary. So let's write the summary. Okay. Now, so what I am getting, GLNC is equal to UN intersection into e to the power HN. GLNR, I am getting this is ON into e to the power SN. Third, I am getting this GL plus NR. This is SON into e to the power SN. Fourth, I am getting something like SLNC. This is equal to SU N intersection to the power SN intersection small SLNC. So SLNR. This is equal to SON intersection to the power HN intersection small SLNR. Now, okay, so this whatever I have derived from previous pages, I have just listed that too. Suppose take G is equal to SLNC. Now take G is, okay, what is the Lie algebra of G? This Lie algebra of G is small SLNC. Okay. Now take G intersection UN. What will be G intersection UN? So G intersection UN is, this is the precisely this matrix complex matrix with determinant 1, and that belongs to UN. So this will be SUN. Okay. So okay. So if IV, you can write that like IV, you can like G is equal to G intersection UN into exponential map HN, sorry, e to the power HN intersection G, where G is the Lie algebra of G. Okay. So exercise. Check that for other groups, the polar other groups means this whatever for all the, okay, for all the groups above, groups rather above, we have G is equal to G intersection UN into e to the power this HN intersection G, where G is the Lie algebra. So this is a polar decomposition, and I am saying that polar decomposition is nothing but precisely G is equal to G intersection UN into e to the power Hn intersection G, where G is the Lie algebra of G. You can check these 5 proofs listed above. So what our goal is now? Our goal is to really determine the generalize this result to what for a general classical Lie group. So our aim now, our aim is to generalize above result for other for, for suitable class level, suitable matrix level. So what do you mean by suitable? You can ask this thing. You see that suitable means these groups are actually are defined by certain set of polynomial. Okay. So what is the meaning? Let us see. See this SLNC. This is nothing but the set of all invertible matrix inside GLNC with determinant 1. And you know that determinant is a really polynomial function. So, and these are given by, so SLNC is given by some set of polynomial. So, and we will see that this polar decomposition will be valid for those groups for which are described by certain polynomial. So let me define that group definition part. Then we will prove a polar decomposition for that group, and that is the most fundamental, one of the very important things. So okay, so now onwards you will see that most of the things are unfamiliar to you. So pay little attention here. Okay, so let sigma belongs to GLNC. So let zeta is a sigma be the ith entry of sigma. Okay. So this entry I will call the coordinate. Okay. I will call coordinate. So sigma has n square complex coordinate. Okay. So that means I can write this zeta is sigma as xij sigma plus iuij sigma. So now I get two more coordinate, real coordinates. So sigma has 2n square real coordinates. Polynomial means this polynomial. Okay, so let us write the definition of pseudo algebra group. Definition. So definition, let this definition I have taken from Helgason. So let G be a subgroup of matrix, subgroup of GLNC. G is called pseudo algebraic group if there exists a set of polynomials p beta belongs to some index at I. Okay, so remember sigma is 2n in 2n square arguments. So G is called pseudo algebraic group if there is a set of polynomials p beta belongs to I in 2n square arguments, so that sigma belongs to G if and only p beta, this entry that means sigma satisfies certain polynomial equation, that polynomial equation 0 for all beta belongs to. So this is called sigma. G will be called pseudo algebraic if elements of G will satisfy a precise set of polynomial equation polynomial P beta. Okay. I will keep this for a few seconds so that you can understand this definition.
So why are you calling it pseudo algebraic?
Actually, I don't know. It must have some connection with algebraic groups, I suppose. But I have taken this, as I said, that from Helgason. So for that reason, that this is a question, valid question, but it must have some connection to algebraic group. Pritham, is it the definition is clear?
Yes, yes.
Jayant, are you there? Jayant Sarkar?
No, he's not.
He's not there. Okay. So one example, let us say. Example first. Okay, so this is suppose actually GLN. Okay, so actually GLNC you can call also pseudo algebra group where you take this beta index and beta is empty. Okay, so that is very
Empty.
key. Yeah, beta I. This is a pi.
Actually, you are taking, so to start with, are you taking GLNC as an algebraic group or what?
No, I am setting GB subgroup of GLNC.
No, so this is my question. Is GLNC as an algebraic group or pseudo algebraic, whatever you are saying?
Yeah, where this I you can take pi. Okay, this is just leave that trivial case. Okay. You can take GLNC as pseudo algebraic group or GLN not a pseudo algebraic. This is upon your definition. But I take this I as empty and then I consider that G is pseudo algebraic. Okay. So GLNR, this sigma belongs to GLNC. So that Yij sigma is equal to 0. Say this. Okay, Ij 1 to n. Okay, so this is clearly a polynomial. So second thing is this is SLNC. This is sigma belongs to GLNC. So that determinant of sigma is equal to 1. So you know that this is a polynomial in Xij sigma. Xij sigma, Yij sigma. So these are example of pseudo algebra group. Now observation. Suppose G is a pseudo algebra group. Then that means G is given by some polynomial. Now G satisfies some polynomial. That means G is closed in GLNC. So automatically this will imply G is a matrix group. So pseudo algebra groups are matrix group. Okay. So now one important thing proposition. Actually, so let G be a pseudo algebra group. Suppose G belongs to GLNC and G prime is equal to G inverse. Okay, then G prime is also pseudo algebra. Okay, so see the thing is this statement is very seems trivial to me. Okay, so you can, if it is not a difficult thing, you can write it down. Actually, what is difficult is really the thing is to write down a proof. Okay, so since this matrix we are multiplying G into G inverse. Okay, so that means this is sort of a polynomial function. Therefore, you can feel that this G prime is pseudo algebraic. But what is difficult is that this to write down the proof precisely. And actually, I think I will write down the proof only for complete.
Hello, Munada, are you there?
Muna has left.
Yes. I'll call him. Yeah, just wait for some time. He is connecting with Geo.
Okay, am I audible now?
Yes, yes, you are audible.
Where?
Yeah, it's not visible.
Who is you?
Are you sharing your screen?
Yes. Let us is visible now?
Munada, is there any problem in sharing the screen?
I have shared. Yeah, it should.
এখন বলতে পারবো না, আমি কাজ করবো তারপর একটু। লেকচারে 3:45 শেষ হওয়ার পর।
Munada, are you there?
Pritam,
Yeah.
so the email ID you used to circulate the mail, that probably is not working because I sent the email and it is not going through.
Oh,
Like that email ID was like discmha@googlegroups.com.
oh, that is no, that is not my email ID.
Okay, so can you provide your email ID?
Yeah, should I tell you now?
Yeah, please tell me because
Yeah,
this
yeah,
chat box I cannot access.
Okay, it's PRITAM
PRITAM
G
G
at
hmm?
IISc.ac.in.
IISc.ac.
Pritam,
Yeah,
are you able to
I can hear you, Munada, but your
you have
voice
to
is
share
breaking.
the screen? Share screen. Are you able to see something on my
I
screen?
am not able to see your screen, just a big M logo. I don't know about others.
But you try to open your video first. I think that's the camera is not working.
Sorry, actually, I think
Mona,
I should.
Mona, can you put on your camera? Is your camera working?
Yeah, that is what I am not on. It is not.
There is a camera
So,
sign. Just click on that.
that on. Yeah.
That is on. That is
I know,
on.
I am clicking on that. Actually, I am using this Geo. That is not working now. Using this Geo internet now because HRI connection is lost now.
I think there is some problem with the network because we can't see
Okay,
it. So
okay.
your camera is not working itself.
Okay, so I got an internet connection at HRI.
Yeah, now we can see.
Now you can see.
Yeah.
Okay. So I think where actually I will take then okay, so will I leave this as an exercise, this proposition?
Yeah, you can leave it as an exercise.
Is there anybody who wants this proof or this
I don't want to see the proof.
Yeah, then I should leave it the exercise. So then I must okay, so let us finish something else. Actually, you just write the coordinate change and then you really, this is believable actually. So let me just stop there now today, or will I give some? Okay, let us keep one more proposition because I have 6 minutes more. Not this is not really a proposition. This is a lemma. Okay, so let Qt is something like j is equal to 1 to n b cj to the power bjt. Okay, this bj belongs to R and cj is a complex number. Okay, so this Qt is really that this is this is called a polynomial exponence function. Remember this bj belongs to R and cj belongs to C. So suppose this q vanishes at every integer or n belongs to z. Then this say then Qt is identically 0 for all t belongs to R. Okay. And proof is also easy. What is the idea of proof? So idea of the proof is you approach t tends to infinity via integers, and from there you conclude that q is equal to 0. Okay. So let us say that suppose qt is equal to cj e to the power pjt. Okay. J is equal to 1 to 1. Suppose I want to take limit t tends to plus infinity or infinity qt. So what really matters in this case to that this will be comparable to some e to the power some constant multiple into e to the power some e to the power mt, where m is equal to this maximum of b1, b2, bn. Pritam, is this clear?
Yeah.
Okay, so this is to the power mt, where m is the maximum of b1, b2, bn. Okay. Now, similarly, if you take t limit t tends to minus infinity, then this will actually become controlled. This will be this is comparable to limit it tends to input some constant e to the power small mt, where m is the minimum of this b1, b2, bn. This is the idea. Okay, so let us do it. So let M is equal to this maximum of so-called B1, B2, Bn. Small m is the minimum of this B1, B2, Bn. Okay. So now if m is greater than 0, this maximum is greater than 0, then I take limit n tends to infinity mod of Qn. So remember, this is like e to the power, this will behave like e to the power mt, where m is the maximum of m, this b1, b2, bn. So if m is equal to 0, that will imply this is infinity. Limit n tends to infinity mod of Qn is equal to infinity. So, but we know that Qn is equal to 0 for any n, for n belongs to 0, n belongs to z. So which is
What did you say? M equal to 0, then what?
for on n belongs to z, we know that this is a hypothesis. So which is a contradiction. Okay. So that will imply this m is strictly, this implies m is strictly less than 0. Okay. Similarly, this if this minimum m is, if this m is less than 0, then you will get that limit n tends to infinity u of minus n, this is infinity, and you know that this is equal to 0 always. So that will give a contradiction. So since Qn is equal to 0, n belongs to z, we get a contradiction. So I have, so m less than 0 is not possible, so m is greater than or equal to 0. So finally I will get 0 less than m, this is minimum, this is the maximum, this is, I have shown that this is less than or equal to 0, so this is less than or equal to 0, this implies m is equal to 0. So that means everything b1, b2 up to bn is equal to 0. That implies that qt is equal to a constant, where c is constant. But since n q vanishes at integers, but since qn is equal to 0, that implies qt is equal to 0. All signals to R. So hence this finishes the proof of the thing. Okay. So this is a important lemma. We will use this thing later, and also you kindly just see this proposition, verify this proposition once more, because we are going to use this thing. Now I think I should stop, and I will take any question if there is any. Is this proof of this lemma is clear, Pritam?
Yeah.
Yeah. So I will stop, and on the next class I will do a very important polar decomposition. Then I will go to pseudo orthogonal group, and then I will calculate the connected component, number of connected components, and this group will be very important for this.
So next class is on Friday, 3:30.
Yeah, 232 or 45 or something. Okay. So is there any question? Is there any question in the chat or?
Hello.
Hello?
Yeah, I have a question. Does this n belong to integer real?
You have to increase your volume. We can't hear you actually.
Something happened here. Yeah, tell me.
Yes, so am I audible?
Yeah, now clearly.
So yeah,
Yes.
I have a question in the last lemma. Can share the screen.
Just wait. Yeah. Last lemma.
Yeah.
This. Yeah.
Does n belongs to integers really matters there, or one can take any separated sequence which goes to minus infinity as well as plus infinity?
Yeah, you can take any separated statement, but here is the hypothesis is that Qn is equal to 0 for n belongs to 0. For that
Yes,
reason, I
but
am taking.
then one may replace n by that sequence as well.
Yes, yes.
Okay, yeah, thank you.
Okay. Yeah. So let us end then.
Okay.
Thanks, Muna.
Yeah.